So lecture 3, random variable. So lecture 3 and lecture 4 and lecture 5, we're going to discuss the random variable, which is one of the most important parts in the probability theory. So lecture 3 is about the very basic things about the random variable. And the topics and contents that we're going to discuss in this lecture 3 are there's 6 things. First, I'm going to explain the basic idea and the formal definition of the random variable. And then after that, we're going to discuss the popular discrete random variable, which are very often used in the community. And then as a summary of the random variables, we're going to talk about the expectation and the variance. And the fourth topic is about the multiple random variable. And then we're going to talk about the conditioning and the independence for the random variable, which is a kind of extension of the conditioning and independence for the events. Okay, first, random variable idea and formal definitions. All right, so the random variable idea. So in reality, many random outcomes, we're talking about the random outcomes, right? Many outcomes are numerical, which means that we can express those outcomes with some numbers. The good example is the stock price. But even if they are not numerical, it's very often convenient if we map numerical values to random outcomes. For example, like 0 for male and the 1 for female. So by assigning those numerical numbers into the outcomes, we can include those things in some kind of mathematical form and expressions, which is very convenient to handle. So the idea is that we have each random outcomes in the sample space. The sample space is basically the set of all random outcomes, and then we're gonna assign or the map the value, the numerical value for each outcomes, like here in the real number line, for example. And that's the concept of the random variable. The good example is that suppose that we have 2 rows of tetrahedral dice. So we have the result of the 2 numbers, like 1, 1. So that means the first row is 1 and the second row is 1. For example, here in this case 4, 2, and so on. So we have a 16 result. And if you define some random variable, which is the maximum of the 2 rows, then we can map some numbers into these outcomes. For example, here in this case, that's the 3, 2, and the maximum of the 3, 2 is 3. Obviously, if you define a different random variable, we can have a different mapping between the sample space and the real number. So as you saw in the earlier example, random variable is a mapping. Let's formally discuss the random variable. Mathematically, a random variable, let's say x, is a something which maps from the sample space to the real line. Here, something is a function. So it's very important to remember that the random variable is a function. Well, sometimes we forget this thing, but this is very important. Random variable is a function. As a notation for a random variable, we typically use the capital letter like X and Y and Z, and the values that the random variable can take is typically represented by this small character. So that's the convention in the community. And different random variables obviously can be defined on the same sample space. For example, you can define your random variable X and another random variable Y and Z and so on. For a fixed value X, that's the value that the random variable can take, we can associate an event. A random variable X has that value. So the fact that some random variable X has the value X, and that's an event. And mathematically, we can express those events as that set of all omegas, random outcomes, such that X of those random outcome becomes the value of X. So obviously this is a subset of the sample space, and the event is a subset of sample space. So we should be able to associate the event and the fact that the random variable x has the value x. Let's assume that values x are discrete. Discrete means that the finite or the countably infinite, such as 1, 2, 3, 4, and 5, 6, for the probability that the random variable x has the value x, small x, is represented by this mathematical equation, right? Obviously, this is too long, so sometimes we shorten this notation into this. The probability that x is equal to x. That actually means this. Well, even we use the shorter notation of the px of x, where this x is the random variable capital X, and this x is a small value of the x. Okay, so throughout this course, we often use this notation, but sometimes we use this notation. For discrete random variable x, we call this pxx probability mass function. In short, PMF. Let me give you an example. Suppose that somebody rolls a dice, then the sample space consists of the 6 random outcomes, 1, 2, 3, 4, 5, 6. And let's define my random variable. X becomes 1 for even numbers and x becomes 0 for the odd numbers. Okay, so everybody knows this example, but I just want to highlight the relation between the event and the fact that the value that the random variable x can take. So we can define the event A1, okay, and that's the set of all outcomes such that the x of those outcomes becomes 1. The set of 2, 4, 6. And that's the subset of the sample space, so that's why A1 becomes an event. But here, in many cases, we use this shorter notation for A1. A1 is just the set of x, 1 becomes 1. But whenever you see this kind of expressions, you should be able to think about this formal definition. Okay? Similarly, we can define another event A0, which is the set of all outcomes such that x of those outcomes becomes 0. Here in this case, 1, 3, 5, and that's a subset of sample space. That's why this is an event. And in a short notation that we are using, like A0 is equal to the set of x becomes 1. Oh, sorry. This should be 0. So again, I want to highlight that the random variable x is a function from the omega to the real number. Okay?